Yes, we'll start discussing Poisson regression. I have a quote here. Once a Nobel laureate, Albert Simon said learning results from what the student does and thinks, and only from what the student does and thinks. The teacher can advance learning only by influencing what the student does learn. So, and that is why I'm so passionate about statistics, and many people, I know a lot of intelligent people, when we say intelligent, highly intelligent people, if they don't, maybe they don't have flair for mathematics, or maybe they have not gotten the secret. So the statistic looks difficult, but it's not difficult. Because you yourself, you know that these people are very intelligent people. It's because they don't know the secret. And one thing with statistics, like what we emphasize in the last lecture on Thursday, is that practice, 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 know and do. It's about doing. It's like a surgery. It's about doing. It's skill. But people don't know. They just think the knowledge. No, you just have to apply it. So it's what you only know what to do. And that is why many people, they come to listen to lecture. When they come to all these practical aspects, so they are not interested. But the issue is that they will forget what even they had. They will be confused because sometimes somebody may present information in one lecture differently, and you see another after a while, you see another in another, the same information in another way. You are confused. So that is why unless you come close to practicing something, from there you now discover, oh, there are some mistakes. Just like this issue we are clarifying now, log linear, you can see in different places. If you don't understand, you discover that there are different. When you see log linear, it does not mean the same thing you knew before. It may be different thing, unless you know that there are different contexts. Unless you look at the context, and those things come by practicing. And that is why we just encourage for you to learn statistics. Practice is inevitable. Poisson regression is a generalized linear model form of regression analysis used to model count data and contingency table. Count data, you can also use for contingency table. We are going to discuss much about that. So we are going to talk about generalized linear model and general linear model, the difference between them. They used to predict a dependent variable that consists of count, given one or more independent variables. So when something is like all these maternal mortality rate now is actually count, number of children that die, especially when that is very rare, especially when it is rare. So like some of those things that are a little bit rare, that are not so common, or as we are controlling, as we are improving our infant mortality, maternal mortality, to actually get the actual value, now you need something like this to actually get it, rather than using linear regression. Sorry. The variable we want to predict is called dependent variable. So it's just like, it has some similarity with linear regression. There are some differences. It has some similarity with linear regression. It has some similarity with logistic regression. I also have differences, from all of them. Now, the variable, just like any other regression you want to predict, any prediction, any regression, form of regression, you are predicting only one variable from one variable or from many other variables. So the variable you are predicting is the dependent variable, otherwise known as outcome variable or response variable or target variable. I also call it criterion variable. Those are the name, or explained variable. So any outcome variable. So the word dependent variable is people that were involved in experimental research in those days that usually use the word dependent variable because they manipulate the environment. So that variable depends on their manipulation. It depends because that's the outcome variable they're measuring that's going to result from what they have done. That's why they call it dependent variable. But the variable that defines the manipulation they did is independent. And other independent variables so that may influence it, they are all independent. But the one you are measuring depends on the manipulation. And that's why they use the word dependent and independent variable. But in observational research, people that are involved in observational experimental research use the word outcome, and exposure. Outcome, exposure. But we know that it means the same thing. In research, what they say, dependent variable, because in statistics, most of the time, the statistician does not know whether you do experimental. Statistics does not respect experimental design or observational design. So what statistics respect is the setup. Are you dealing with type of variable you measure? Is it only one group or two groups or several groups? Though if there are more than one group, are they paired or independent group? Those are things statistics understand, not whether it was you did experimental design. So it doesn't, because the experimental design itself does not enter the statistics. So it's we that try to explain it. Now, the variable we want to predict is called the dependent variable, as I've said. Response variable, target, explain variable, criteria variable. That's the other name. The variable we are using to predict value of the dependent variable are called the independent variable, or predictor, or explanatory variable, or regressor. In case of this regression, and regressor, or determiner, or factors. Those are the other names for independent variable. Having carried out a Poisson regression, you will be able to determine which of your independent variable, if any, have statistically significant effect on your dependent variable. For categorical independent variable, you will be able to determine the percentage increase or decrease in outcome of one group. Almost like the way logistic regression is. For continuous independent variable, you will be able to interpret how a single unit increase or decrease in that variable is associated with the percentage increase or decrease in count of your dependent variable. Our dependent variable now is count. Then it can be count per unit time. That would be rate. So it's used for both. Either because when you say it can be in space or time, you may say that how many how many children, what are the factors that determine the number of children in the family? In that case, you may not be specific about the period of time. You are talking of each family now. So it's still can. Sometimes you may specify number in 2 years. So whenever time comes in, become rate. But it's still the same, it's working together. Like that's why we talk about all these infant mortality rates. So this is the best way to actually predict them. Now, the Poisson regression assumes the response variable Y has a Poisson distribution. It follows a Poisson distribution. Because for linear regression, there's an assumption that the outcome variable follow normal distribution, or the residual follow normal distribution. But this one, there's an assumption that the outcome variable follow Poisson distribution and assume the logarithm of its expected value can be modeled. Just a minute, sorry. Just a minute. Good evening, sir. Yes, sir. How are you? I'm fine, sir. Good, sir. No, mi wà lè ṣàpè ẹ̀nẹ́ wá sí Abuja ní ọ̀sẹ̀ bí ẹ pè mí. Okay, that's fine. Okay. Okay, thank you, sir. Okay. Yes, sir. Sorry, it's one politician that was calling. He now call me back. So it won't be right honorable. I'm very sorry. Because if I didn't, it's difficult to reach them. You call, their phone is off. So Poisson regression, I will not receive any. I've silent my phone now. Assume the response variable y as a Poisson distribution and assume the logarithm of it. Okay, we talk much about the logarithm because the logic behind using logarithm we discuss it. So this Poisson regression model is sometimes known as log linear model, especially when used to model contingency. We look at it easy also. There is something I just want us to look at, Poisson process. You may encounter it somewhere. What is Poisson process? So sometimes when something follows Poisson distribution, so alternative derivation of Poisson distribution is in terms of stochastic process discussion word informally. Sometimes these mathematicians, they use some word. When they say something stochastic, it doesn't mean they're random. The word random is just stochastic. So when a random event, suppose the event occur randomly in time such a way that the following conditions are obtained. So this one now is an event that occur randomly. It may not be necessarily, to them, may not necessarily be an even count in an event, something that happened randomly. The probability of at least one occurrence of the event in a given time interval is proportional to the time, length of the interval. What we are saying, like for example, now, if somebody stay in a garage or an highway, you say, okay, is the probability of a car, what we are which one fun car that is very okay, maybe G-Wagon, that is not common. Probability that the car that pass is G-Wagon. The cars that pass will be, but the probability will be the number of G-Wagon divided by the total number of cars that pass. So what is saying that the probability that a G-Wagon pass will depends on the interval of time. Yes, if within 1 hour and within 3 hours and within 5 hours, you can be sure that the 5 hours will more likely, though you may more likely see than 2 hours. So that's what that first statement means. The probability of at least one occurrence of the event is given in a given time interval is proportional to the length of interval. The probability of 2 or more occurrences of the event in a small time interval is negligible. That is, if like for the G-Wagon we are talking now, if we not okay, within 30 minutes, probability of G-Wagon, how many that we have 2 G-Wagon, is going to be negligible. If something is rare, so you now say probability of more than one of it, even occurring within short time, is very going to be small. The number of occurrence of event in a disjoint time interval are mutually independent. When we say something are mutually independent, that is, they may be different. I mean, the probability that today G-Wagon pass and tomorrow G-Wagon, another time G-Wagon pass within 1 hour, they will not be related. So then the probability distribution of the number of occurrence of event is in a fixed time interval is Poisson mean mu lambda t. So the average, you're going to see something peculiar about Poisson distribution. You're going to see that the mean and the variance is the same. So here now, the lambda rate of occurrence of the event per unit of time, and t is the length of the time interval. So a process satisfying these 3 assumptions listed above is called Poisson process. So just for mathematical this thing. Don't worry. Let's go to this Poisson distribution properly. It was named after a French mathematician, Simeon Denis Poisson. So I was talking with somebody on phone, discussing, I was talking Poisson. My wife now said that Poisson, as if you are speaking French. I said, actually, it's French because the word Poisson, as if it's French word. I see the person that even the mathematician that described it, that the name after was a French, Simeon Denis Poisson. A discrete probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time or space. Now, look at the formula. Though I don't like projective formula, but this one looks is a little bit simple. It's not. We're going to solve one problem, just short problem, for you to see that it's very simple. Now, here, some of us have not listened to our maybe you were not in a lecture on probability distribution. Discrete, we have probability distribution. What does it mean? Is the listing of all the possible value of a variable, a random variable. Well, they call it just variable. All the possible values and their probabilities, probability distribution. For example, now, we usually use the classical approach for people to understand the meaning. So, because you need to conceptualize probability, what does it mean? You know, in our lecture on distribution, we talk about distribution as a pattern of occurrence of variable, pattern of occurrence of values of variable in a data set, distribution. And it can be frequency, can be relative frequency distribution, or cumulative relative frequency distribution, or relative cumulative distribution and cumulative relative distribution, 4 different types. When it is the number, just the number alone is frequency. When you now standardize by calculating percentage, that's relative. Relative, when you express as percentage, standardized relative. When you are adding that, somebody, Dr. Yemi, mute yourself. So when you are accumulating it as successive, or you are adding it, that's cumulative. So that's distribution, but probability distribution is close to the, but it's quite different. Here, now I'm talking about pattern of value of possible value of a variable, possible value of a variable now, and their probabilities. For example, if let's use classical approach. If you drop a coin, you say, what is the probability of it be head? You know that it's 1/5, 1/2, 0.5, K 0.5 also, because there are 2 possible sides for the coin, and it can all drop on any of them. So we say half. So the probability distribution for a coin, for one coin, tossing on one coin now, is heads 0.5, K 0.5. That's all. That's the simplest things you can see. Just like a probability distribution of, as we are here in Nigeria now, sex of Nigerian citizen, either female or male. So from our last election, we may know that one is not classical approach. Now that one is relative frequency approach. From last election now, we know maybe the ratio is 0.5, 0.5, or 0.48 for male, or for female, 0.52 for men. Because in the last election, it's like slightly, the men are more, slightly, that's what is there. So that is a probability distribution. It gives you the possible value, either male or female, and the probability. You know, binomial is just the smallest form, 2 possible value. If you are talking of maybe, okay, what's the probability distribution of geopolitical, somebody geopolitical, so you belong to, there are 6 geopolitical, so in this country, and from the maybe last census, we may look at, okay, what's the proportion of the northwest, north central, northeast, southwest, southeast, south. You know, when you do probability distribution, you list all those geopolitical and the probability percentage of each of them. That's probability distribution. You see this example I've given, and the example of discrete probability distribution, in the sense that you can know all the possible value. You know all the possible value or geopolitical zone in Nigeria 6. Even if it is ethnicity, you know, even these days we are plenty, but we have a way of saying, okay, even if we are 200 or 300, we can always say Hausa, Igbo, Yoruba, and others. The issue there is that there are these three categories. You know the category, you can now calculate. If you know the category, different category, you can calculate the probability. That's discrete probability distribution. Is a type of probability distribution where it is possible to know the possible categories and their probabilities. There is another type which is continuous probability distribution that is not possible, like blood sugar now. How many possible blood sugar can somebody have? It is because it has decimal. You may say 60, 60, between 60 and 61, you have 60.11. 0.099. Even between 60 and 61, there are infinite numbers. So for continuous variable, you follow continuous probability distribution because the single fact that you cannot know all the possible values. You cannot know all the possible value outcome for you to even calculate the probability. So what you can do in the continuous probability distribution is for you to know the probability of a range of value. You cannot know the probability of a particular value of a range of value. I don't want to delve into that now. So if somebody is maybe doesn't understand the concept, go and watch our video on probability and normal distribution. It's well spread out there. But why I just went into time to explain this is because of the word discrete probability distribution. So Poisson distribution is a form of discrete probability distribution in the sense that you can know all the possible values within, between two, a space of time. Yes, a space of time within time interval or a space within the space. You can know all the possible value. That is why it is discrete probability distribution. I think I've explained that. Now, you will see that the functions here, just look at the formula, the function x just means the number of times that thing has happened. The rate. Does it maybe within this short time? No, it did not happen. That would be 0, 1, 2, 3. To infinity can be 1 million times, whatever. So it ranges from 0 to infinity. You cannot say, it cannot be negative because you cannot say how many times something happens, say negative -2. No, number of times something happens, rate, it cannot be number of times something happens, cannot be negative. So you see, but it can be 0 if it didn't happen, can be 1, can be 2, can be 3, like that. So that is why it's integer up to infinity from a 0 possible value. Then the lambda is the mean number of occurrence in the interval. Within that interval, what is the average number of occurrence? That's the lambda. Here now, that is the parameter you are estimating. That's the parameter you are estimating. Of course, you already, because the x, the number of times the thing happen, you can collect the data on it. The mean number of time now is the lambda. Then this E is Hiller's constant. It's a natural, they call it natural constant, 2.71828. So the origin of that, you can go and search it out. It's not for this time. But those are the things they use for non-natural logarithm exponential. The value is a constant that you use. So if you look at it now, the probability of an event happen in X number of time, that is the rate now, maybe 1 or 2. That's what we call X is a particular value here. Is lambda raised to power X. Can you see the lambda, the mean? You want to calculate the mean number of time raised to power X. Then this natural constant, Euler's constant, raised to power minus lambda over x factorial. You know the meaning of factorial. If it is 2, 2 times 1. If it is 3, 3 times 2 times 1. If it is 9, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That is what the meaning of factorial. Now, because somebody was, okay, let me just, before I differentiate, let's do further one. So, just to look more further, probability distribution of the number of events which occur randomly and independently in time or space or somewhere. Average rate. For example, the number of deaths in the town from a particular disease per day, or the number of admission to particular hospital typically follow a Poisson distribution. Can you see number of admission? You know, sometimes when people you feel that there's a facility, people are not admitted again, or people are not attending the or too many people are attending, you can cope with a lot of issues. So, especially if you want to size hospital now, and in that environment, you want to see, some people want to see, some hospitals in that environment are not viable. What is the factor? So why will you go and start your hospital in that place where nobody come to that place? You may want to know factor that determine the number of people that attend or the number of admission or whatever. That's the best model to use. So it just for you to do literature review of many factors. How do they affect the number? No, many factors. We are not talking of that now. So just try to give an example of example you can use situation where you can use Poisson distribution or regression. The Poisson distribution variable is the count of the number of events that occur independently and randomly in time or space at some rate. The Poisson distribution function is PS. This mean is the mean. That's what we have already said before, the mean. So here now, I use, instead of mu, I use lambda. Instead of lambda, use mu here. You will see, sometimes you read some literature, it put mu. Sometimes they put lambda. It's good to know that you may encounter it like that. So it's the same formula. The E raised to power, if you look at it, this one was in the back, this one was in the front before. No, I said that the lambda raised to power x times the constant raised to power minus lambda. That's what. So you can see minus lambda, constant raised to power minus lambda times lambda raised to power x. So instead of using mu here, you use lambda. It's the same. So that is why it's good to even look at it in different ways, because you are reading an article, you see that it's presented, just for you to know if it's correct or not. Then over x factorial. The symbol, I think I've explained the factorial. So the mean is the expected number of occurrence is sometimes seen as lambda, sometimes called the event rate or rate parameter. So is the expected. I don't know if some people have heard me talking about the mean is the crudest model. It's an expected value. We say expected value is the value when non-hypothesis is true, and mean is the crudest one. Here now, we are using the mean rate of occurrence as the expected value. That's the expected value. Look at the graph. Depending on lambda, the mean, look at the shape of the graph. The shape of the graph is different from normal distribution, but as the mean increases, it approaches normal distribution. You know, almost all distribution, the way I see it is that normal distribution is just the one you are seeing. It's more like the physical. But hiding under the normal distribution are many other distributions. What you just see physically, the one that is most obvious in normal, but all of them are related to normal distribution. All of them. We talked about chi-square yesterday that is related to normal distribution. The person that first described chi-square, what did he do? He square z score. He says z distribution. He square it and it became chi-square. He removed negative. You know, in normal distribution, the mean is in the middle is 0. Standard normal distribution, the mean is 0. In the middle, we have negative side. We have positive side. So if you square them, all the negative will become positive. Everything positive will remain positive, negative will become positive. So that is, it will be skewed. And that was how we discover calcium. But as the degree of income increases, which may be related sometimes with to the sample size, but not all the time, the chi-square approaches normality. The same thing with normal distribution. As the degree of freedom increases, approaches normality. The same thing with F distribution. As the degree of freedom increases, approaches normality. The same thing with Poisson distribution. As the mean increases, it approaches normality. As an example here, for us just to, this one is not something we are running with experts, just an example, just for us to understand Poisson distribution, because Poisson distribution is very, very important for you to understand Poisson regression. Once you just know that, at least the basis of it is Poisson distribution. As an assumption that the variable you are trying to predict follow Poisson distribution, and that's what I'm trying to make it for us to be able to conceptualize this Poisson distribution. Now, the average number of cases of Lassa fever in your community is 2 per year. What is the probability that exactly 3 cases will occur in the community the following year? So, mu average number per year is 2. That is why the mu, that is the lambda, is 2. Average number of cases per year historically. Yeah. X 3 is the number of expected cases now you are expecting. Then the Euler constant. So if you just feed in the formula we talk about, it give you 0.180. That's 18%. So the probability of 3 cases occurring the following year is 18%. 0.18. Very simple like that. Now, before we now proceed to other things now, to discuss generalized linear model, somebody, because Dr. Abasi, has Dr. Abasi come? Is he around? Because when he was talking about his expectation, he has not joined us. What happened? He talked about something like a binomial. So how does Poisson distribution relate to binomial? What's the relationship between them? Binomial distribution, you know that the outcome variable is a discrete probability distribution also, like Poisson. But this one, the outcome is not, maybe is either of the 2 possible outcomes. There are 2 possible outcomes. But this one there's not like 2 possible outcomes. But that one, there is 2 possible outcomes. And there, the number of trials is surely limited, because when you are trying to calculate for binomial distribution, the number of trials, that is sample size, is more like a fixed one, is limited, and the probability of success is higher than that of Poisson. Poisson distribution is more appropriate for variable than, number one, you have large number of trial. The probability of success is very rare. The probability of success is very, very rare. So if the probability of success is very rare, so okay, it look one, if it happens, just happen. You know, it's just like the issue of staying in one place and try to see if a particular area car, how many of that area, or even if one just happen. If it's very rare, you can even stay there for 1 week, you may not see one, or you just barely see one. How many have you counted? The number you have counted that are passed before you see that one will be the sample size, the trial. So somehow is related to geometric distribution also. Geometric distribution is a discrete probability distribution also. That one also, the number of trials is very high, but the number of success is very low also. But in geometric distribution, first success after many trials. But here, It's more like rate. It's not the first success. How many of those occurring events occur within that time interval? So that is Poisson, and that is why Poisson, because of that time interval, the rate, that's why it's most appropriate for rate. Now let's quickly. Okay, is there any question before I move to the, because this is not a normal lecture, this is workshop. Even though we are going to look at the example, but let's be sure that we get the concept right. Any question in what we have discussed? Concerning what we have discussed? No question?
Hello? Hello?
Okay.
I'm listening.
Hello?
Sir. I can hear you, sir.
Must it be for events that are rare? For example, in the National College, the number that passes part one, primary,
it doesn't have to be rare.
Usually very rare.
It doesn't have to be rare, sir. But what is here that is most of the time is rarer than that of compared with binomial distribution. Hello?
Yeah. I was just using the example.
It doesn't have to be rare.
Of the National College.
Yeah, okay, go on, sir.
The pass rate in primary is very rare, but at the primary level, but the pass rate in part 2 is very high.
Okay.
So can we use it both for primary and part 2 to try to see the probability of passing? The probability of passing primary in National College is very low, but the probability of passing part 2 is very high.
Yeah, the number of people that pass. Well, you can use it, doesn't really matter. Okay, we are not explaining the reason the pass is very low and high now. That's not the reason. It's the appropriateness of using. Yes, you can use to model what are the factors that are responsible for the rates of passing, or failing in the 2 exams. You can use it. You can use it.
Okay.
I can tell you.
It's appropriate.
Yes,
not just the appropriateness.
Yes, it's appropriate. So in this case now, yeah, you are talking of how many people pass here, the pass rate. Yes, but if you look at it, logistic regression may do the same thing. Do you know why? Maybe you know what? Though sometimes also you may, because there's a data here, one of the data we are using. We can actually compare the performance of logistic and people have and Poisson, and discovered that the Poisson is better even in the situation where you use logistic. Because your rate usually put it over 100. Your rate, where, because I understand what you are not saying now. So you can use it, but sometimes you may even discover it's better than the logistic. Because if you look at the logistic, it's perfect example because it's bonded. They usually use over 100%. The pass, you are talking of pass rate now, you see, over 100%. Because the relative is rare. It's a relative issue. When we are talking of rare, if you look at maternal mortality rate, why do they use it? Because they know that if you put it over 100, you are going to get 0.000 something. That's why people use over maybe 100,000.
100,000.
But something that you can still see number of people that pass within 100 people, over 100. Statistically that is not rare. I don't know if you understand me now. It's not rare. You just say it's rare. They were talking of in a situation where when thousands of things have occurred, have gone, we've not gotten success. We have not even gotten anything with the research you are looking for. Millions or thousands, many thousands. That's what we call rare event. In a situation where 1 of 100, or 2 of 100, 10 of 100, 10% is not, statistically is not real like that. But you are just saying it's real the way we are looking at it physically. But it's good because as you're going to see, it may even be a better predictor. It's a model to predict the pass and failure pass rate in exam. Okay, any other concern? Okay, let's now, with the first I said that Poisson regression is a form of generalized linear model. So let's look at what is general linear model, what is generalized linear model. Usually, general linear model refers to conventional linear regression model for continuous response variable given continuous or categorical predictor. What he's saying is that whenever your outcome variable is continuous, the exposure can be categorical and can be continuous, but the outcome, when it is continuous, you use linear model, general linear model. So under it, the multiple linear regression, ANOVA and COVA, these are under general linear model. Then generalized linear model. You know, just forget about this GLM. Many people, they mix it together. They can write general linear model and call GLM. They can write generalized linear model and write GLM. Some people try to differentiate. When they now write generalized linear model, now get GLIM, GLIM for generalized linear model, and I use GLM for general linear model. So people use GLM for even generalized linear model. So when you are reading GLM, you have to know which one are they talking about. So it's the generalization of the linear regression model that allows the dependent variable that is not continuous variable to be related with the independent variable through a link function. Can you see? The real general linear model, the outcome is continuous. But in a situation where the outcome is not continuous, how do we now use it? Use the linear model. So if you introduce a link function, it will now allow you to now use linear model to predict not continuous outcome variable. So generalized linear model has three parts. The random component, which is the response variable. That is the outcome variable, is the response variable. It's the random component. That's the outcome, is the variable of interest. That's why they call it random. It can be any value. That's what it just means. The random, the one you don't have, the one you want to predict. Then the systematic component, which is the linear predictor. Systematic. The word, why should they use the word systematic? Because that is the one that the component that is in the result that is helping you. You have the value you want to use to predict the other one. That's why they use the word systematic. The link function, which is the key connecting the two of them. Now, look at the table here. We have the list of this model now. Linear regression, ANOVA and COVA, logistic regression, log linear, Poisson multinomial response. Look at their random random component now, which is the outcome variable. Linear regression is normal. ANOVA and COVA, they are normal. So if you look at they are the one under general linear model. So when we say generalized linear model, doesn't mean that those ones that are general linear model, they are not part of it. It's an extension. It's just like you have a office now, a complex you are using it for something, and you want to accommodate some other function for, and it's not appropriate for them. You now extend it and now bring in some gadget that will be able to incorporate those other functions. So still in the same complex, the initial one is still part of it also. It's not even maybe. So when we say, when you say extended extended setup, the extended setup is still accommodating the old one and the new one. So that's why when we talk about generalized linear model, even though general linear model, they are part of it, they are part of it plus some other that were now brought in through a link function. So now you see linear regression and COVA and ANOVA, their random component is normally distributed. Logistic regression, the outcome is binomial, that we are talking about binary logistic. Then the log linear, is Poisson. Poisson itself is Poisson. You're going to see, because there's a special form of Poisson that's log linear. That's why you see this thing. And that's the first one we're going to run. Now, multinomial is talking about multinomial logistic, which is multinomial, or the random, this is multinomial also, the random component. The systematic component now, for linear model, the systematic, continuous, then though, well, it's continuous, but in real life, you know that it's continuous, but you can incorporate categorical also. Categorical can be there. And in that case, you create dummy. That was the question somebody was asking. The dummy will make it to be categorical to behave as if they are continuous. Then ANOVA, you know, the systematic part is categorical. You know, when you are looking at, you are comparing the mean of 3 or 4 groups. Group itself is the group variable, is the exposure, is the systematic aspect, is categorical. So ANCOVA is mixed. So because ANCOVA is a blend between regression and ANOVA. So ANCOVA, if you look at it, the ANOVA, the categorical, the exposure variable is categorical. But when you now bring another covariate, that covariate is a continuous, it's not categorical, it's a continuous variable. We want to see the effect of another continuous variable. So in that case, you are now having mix, both continuous and categorical. That's what you see by mix here. Logistic regression is mix. Even actually the linear regression also is actually mix. Then, because you can incorporate both categorical and this thing in the exposure. Then log linear, the special form of that Poisson is categorical. The exposure is categorical. That is the reason they call it log linear. We'll still explain it. Poisson is mixed, just like we're going to have the case, we're going to have exposure that are categorical, Then multinomial is mixed also, just like multinomial logistic is mixed. So let's look at the link functions. So you see for the first 3 that are initial family of general linear model themselves, is identity link is identity. What it just means that they are all something just to identify. It doesn't change anything. It's just they still carry their initial the way they are. So the link function is identity. Identity just to identify that, oh, you are there, just like formatting. It doesn't change anything, just to identify them. That's why they just use the word identity. The link, there is no function. The function does not change anything. Now, logistic regression is logic. We're going to, okay, no room for, well, we may still discuss it because we are not here for logistic regression. Logic means the log, you know, for some of us that were around for logistic regression, logic is logarithm of the odd, and odd is probability over 1 minus probability. So logic, that is the link function for logistic regression, is logic. Then we have log linear. The log linear and Poisson, the link function is just logarithm directly. We're going to see now multinomial not is logic, also generalized logic. It's still logic because it's a form of logistic regression. So I think we are getting this one. This one just to create a pictorial view of 3 of these generalized linear model family: linear regression, logistic regression, Poisson regression. Look at the graph. The other one, naturally, the way any distribution, the one that follow normal distribution, because the residual we follow normal distribution, will be on a line. And you see, will be on a line, will be linear, the residual. Anyway, some of us that were around during the time of the linear regression, we explain all this in detail. How do we get our our line, regression line. If a logistic is sigmoid shape, and this one, look at the way it is. No, it will first of all be slow, later it will jack up. So Gaussian here just mean normal. Now, just to create a, so type, let's look at the variables now, type of variable types. For Poisson now, that's going down to Poisson, variable type for Poisson. In Poisson regression, response or outcome variable, Y is a count. We have already said that. And the count cannot be negative from 0 to infinity, integer, whole number to infinity. But we can also have Y per time, per unit time. That is, you specify the time, that is the rate or incident. As a response variable, where T is an interval representing time, space, or some other grouping. That's for explain variable. Explain variable means the response variable. For explanatory variable, explanatory variable, that is the independent variable, X, can be 1, 2, 3, to as many as possible. You can accommodate in your model. So it can be continuous or combination of continuous and categorical variable. Convention is to call such a model Poisson regression. That is, when you have the outcome variable is a count or rate, but the exposure variable can be combination of continuous, can be continuous or combination of continuous and categorical. Poisson regression. Now, there's a situation. Look at this bullet, the second one. Explanatory variable where all the explanatory are categorical. So then the count to the model are count in a contingency table. So when you now do it, you can use contingency table. So the convention is called log linear. That's where the name log linear is there to. So they usually call it log linear. But well, that's not, to me, that they just call it by convention. I don't think that's the reason the name is that, because the reason go log linear is because you are going to take logarithm. We're going to see that we're going to take logarithm. That's why log linear, but they call it whenever all the categorical variable are, all the independent variable are categorical. This is called, in Poisson, they call it log linear analysis. Log linear, they call it log linear model. So a Poisson model, a Poisson model where all the explanatory variables are categorical, it refers to a log linear model. Then if it is a rate per time, that is the count per time, the variable of interest is also called, irrespective of whether they call it Poisson. Even if all of them are categorical, it's called, once the outcome is a rate, it's called Poisson. So you see, there are three key scenarios of Poisson regression here. It's one of them that is called log linear model. Just to create a meta picture. So if you plot the graph, this is linear, the first graph is linear, this one is Poisson, you will see that that is the orange line, and I try to, for each value of X, try to look at the distribution of the residual around the regression line. You will see that for linear, one of the requirements is that the residual should follow normal distribution. And you see, you will see the shape of the distribution around the line for normal, the first graph is normally distributed. For this one, for Poisson, is not, but as the mean increase, the S increases, it becomes to look like normal. Look at, to confirm it, look at it. This first one is OLS, that is for linear regression. This one is Poisson data. Can you see the distribution of the residual around the regression line was, can you see, skewed? But as the number of S increases, the value increases, it becomes to look like normal. So I think we have explained that. So when we are now talking of for rates now, random component R respond Y as a Poisson distribution, and T is the index of time or space. More specifically, the expected value of rate will be Y at T. So it's going to be mu. The mean value will be mu per T. The rate now, the lambda, that mu here is the same thing as the lambda at the time. Systematic components, any set of the variable with the limit function, and the limit function here is the logarithm. So Poisson linear regression model for the expected rate of occurrence of event is this. So what is, if you look at it, look at this right side of this equation, alpha plus beta x. This one is an assumption that is only one explanatory variable here. Alpha is the intercept, beta is the slope, x is the explanatory variable. So if we were to be linear, okay, we're going to show another slide that if we were to be linear model now, it just y, just put y is equal to alpha plus beta x. But we cannot use for logarithm, for rate, it got to be logarithm of the rate. Lambda, that is the rate of the average, average rate or whatever of the event. So it's logarithm, because logarithm is our limit function. Go to calculate the logarithm. We're going to do it with our data with ARM before we run it. So if you rearrange it like this, this one is mathematics. So for, just in short, logarithm Poisson regression model is log lambda B0 plus beta S B1 S1. You know, alpha is the same thing as beta 0. The intercept is the same thing. So you either use as intercept, or you use A or alpha, or you write it as beta 0. The beta 1, x1 will be for the first variable. So this one is assumed that there is only one variable, explanatory variable now. But if we have two explanatory variables, it's going to be plus beta 2x2. If there are 3 plus beta 3x3, just know that the Poisson regression model contains no separate error term as seen in linear regression, because lambda, which is the average, is both the mean, determine both the mean and the variance of a Poisson random variable. What we are saying is that the mean and the variance is the same, unlike in normal distribution. You know, in normal distribution, the mean is 0 and the variance is 1. So, but in Poisson distribution, the mean and variance, they are not, they are the same. It's the same thing. They are not different. So let's look at, well, before we read this one, it may not be necessary. Interpretation, this one can even confuse people. Interpretation of parameter estimate. When you do the, well, is a food for thought. If you do, we have already said that beta is the regression coefficient. If the regression coefficient is 0, the exponential of 0, the opposite of the logarithm. No, we are going to, when you calculate the logarithm, when you finish, you now calculate the opposite, you have to reverse by exponential. Will be 1. If beta is less than 0, which is, that is, if it is minus something, the exponential will be greater than 1. If beta is greater than 0, exponential will be less than 1. Yes, the exponential will be less than 1. Now, yes, if beta is less than 0, sorry. The second one is beta is greater than 0. You know, it's the same thing we do in logistics. Now, there's nothing there. If the beta is negative, minus something, it means that it's less than 0. The odd ratio, which is the exponential you're going to calculate, will be 0 point something. It's going to be less than 1. But if beta is greater than 0, that is positive value like 2, like 3, anything that is positive, the odd ratio will be greater than 1. And if beta is 0, the odd ratio will be 1. That's the exponential. That's just that one. I think we'll go to the practical now. I'm sure some people, people are not sleeping. The last slide before we now practicalize it, started with the practical, is assumption. What are the assumptions? Some of those assumptions, we have already discussed them, almost all of them, just to gather our thoughts. Your dependent variable consists of count data. Yes. It's a count data. It's not continuous variable. It's discrete. Number of this, number of people that attend our class is best modeled with Poisson regression rather than what are the factors that determine number of people that are afraid attend our class. You have one or more independent variable which can be measured on continuous, ordinal, dichotomous. That was the general thing. Then you should have independent of observation. That is, the observation should be independent. Then the distribution of count, conditional on the model, follow a Poisson distribution. And that is the outcome variable where it's more like repetition of number 1. The mean and variance of the model are identical. So there is a way of checking this assumption, but I will not bother ourselves. Maybe that will be for another time because a lot of complex things involved in checking these assumptions, some of these advice, especially this last one. But what we just do, because by the time we run in, we go to see some deviant likelihood ratio, all those stuff. They will go straight to the what do I call it? To the table interpretation. For some of us, the interpretation is very straightforward, just for us all, because once you understand how to interpret odd ratio with logistic regression, this one, there's no much different. There's no even different. There's no different. So we have an example. The first example here, look at, is an example. I don't know, before we start that, any question on all this talk? Any question?
Look at the charts. Look at the charts.
Okay. Is it this one or the first one? Is it this one or this?
No, I mean the
charts. Okay,
no,
sorry,
I mean the question on the charts.
Okay, sorry, sir. When you say chart, my mind just went to this. What variable does it assess? What variable does it assess? I don't know which one. I don't know which one you are talking of.
Does Poisson assess?
Poisson.
Variable Poisson assess. Yes.
Is it assess or predict? Because it's a regression.
Okay.
Regression, you know, in regression, you are predicting a variable, one outcome variable from some exposure variable. It's just like linear regression, logistic regression. So maybe the question I'm asking is that we have said that it counts variable that is number of something, yes, number of something or rate. If you say number, like what factor, if you want to predict what are the factors that are responsible for the number of people that attend a class, the number of people that pass exam, the number of people that are hospital admission, all those things. What are the, like even attendance in the clinic, number, attendance rate, what are the factors? Is best predicted with Poisson rather than linear regression. Is it clear?
Yes.
You are not the one that asked the question anyway. So it depends on the question I'm asking.
Yeah, but
yes, sir, it's clear, sir. Thank you, sir.
Okay.
Yeah, all of us.
I know, but I want the person to, because if it's clear with the organization, it's not clear with somebody that asks the question. Okay, you mentioned it act like regression and can be used to predict. Is it numerical or category? Okay, I think it's still say the same thing. I think this second one also is clear. Somebody is talking. Want
Yes,
to talk?
sir. Yes, sir.
So there's another question. Which is the residual? Okay, I think this issue of residual, we talk about residual in this one does not have residual. You don't model the residual in this one. But you say which is the residual? The residual is when you have determined, when you create a model with the explanatory variable, independent variable. To when you have predicted, you predicted the dependent variable. When you now slide to see, it may not completely predict it. And the remaining one will be the residual. I don't know. Is other people having problem with residual? So that I can just open the slide for normal linear regression. I just show that place so that you see, you look at, have a meta picture.
Yes, I don't mind this. I don't mind the lesson.
Okay, you don't mind it. You have forgotten the one we have done.
No, I actually remember. But because of exam.
Okay, let me just show. Let me just show it. Because we have the mental
Picture.
yes, we show it because some of those things better you show the picture rather than just talking. Yes, this is. Okay, I don't know if I've shared. Can you see? Can you see this? Can everybody see?
Yes, sir. Yes, sir.
Yes. What we are saying is that when you have done your model, this is a model, this is the linear model now, regression. But each value, there are many. Yes. Let me show this one. This is the line, the regression line. That's the model. But you know, the scatter plot, the point you are seeing is where X and Y meet. For each value of X, what is the corresponding value of Y in your data? So for each person, maybe this is Florence now. What is the X? What is the Y? Where they meet, the Y is on the Y axis, the S is on the horizontal axis. The Y is the outcome, the S is the exposure. So where they meet, those are where the scatter plot. When you now draw the model, since all of them are not in a straight line, and it's you are modeling with straight line, when you draw the line, of course, we have already talked about the best line is the line of best fit, and the method of least square is the best. The method that minimizes the distance between each and the regression line. So what you see here is that as you draw the line, some may be on the line, the majority will not be on the line because they are scattered. Now, you are having two values. The value you are seeing there is the observed value, the dot. But where that, if you draw a perpendicular line from that to where it means the model, that is the value the model predicts for that person. That is the predicted value for that person. So for each of these now, you draw a perpendicular line from a dot. The dot is observed value. That's what the data you capture from the feed. And that's what the where X and Y meet. But where if you now draw a perpendicular line from that place to meet the regression line, that point will be what the regression line, the model predict for that person. So the difference between what the model predicts and what you observe is the error. That shows that the model does not perfectly predict each value. The difference is the error. And what we are saying, if you look at it now, you see, because in a model, in linear model, if it's a good model, the average distance between if you look at it, some value will be above, some value will be below. Because there are some, the the model predicted higher value than what they observed is. Some, the model predicted lower value. Those are the ones that are up. So the difference now is the observed minus expected. In a situation where the observed is greater than the expected is what the model predicted. When the observed is more than expected, the error is positive. When the observed is less than the expected, the error is negative. Those are the ones below. So, and that is the logic behind squaring it, because if you add both of them, it give you 0. That's why you square. When you square it, it gives you, that's what they call it, method of least square. The method of least square is the method in which, when you draw the line, the best line will be the line when you square the difference, the error, it will give you the smallest value. If you give the same scatter to many people to use hand to draw, you can draw different things. If you try to measure the difference between your line and each from and now square them, the person that is the smallest when you sum it together is the best line. That is why the method of least square. So the error, I think there's a place where I think I showed something on almost scarcity. Yes, yeah. If you look at it, look at here now. If you look at this first one now, if you draw the line now, you see that the error in the load, if you draw the line in the middle for this first one, the distance between the line below and those error below and this thing is constant along. There's this homoscedasticity. That is, the error, they are constant along the line. While this one, the errors are not constant along the line, is heteroscedasticity. So in a good model for linear model, the error will be homoscedasticity. And if you now try to do the error along the line, follow normal distribution around the line. But in this heteroscedasticity, it will not follow. So that is what I just explained. I don't know if that one has thrown some light to what we mean by error. Has it thrown some light to what we mean by error?
Yes,
So the error is the same thing as residual.
Residual, yes. The error is the residual. The residual. So
go back.
And that is why, can you see now, for normal now, we know that the error is usually constant, is following normal distribution, while in Poisson, it is when the sample size is increasing, the mean is increasing, that we now look like normal distribution. So, any other question? No other question, okay? Yeah. Now, let's look at an example. That during 2 treatment regimen, the number of patients to say the quantities were assessed. The data are summarized in the underneath 2 contingency table, 2x2 contingency table. To say the quantity is an uncommon type of ventricular tachycardia. It's just a ventricular tachycardia, a case of ventricular tachycardia. So there's some treatment for maybe for heart disease, for something, but the side effect of the treatment is ventricular tachycardia. So now we want to see the outcome measure here is to say that is ventricular tachycardia. This is an example of log linear in the sense that we just use one linear and one variable, one exposure variable, because that exposure is categorical. So when the exposure is categorical, and in this case also, it look as we said, okay, is there to say or no to say? So in this case now, it's not actually talking about the number of to say, is whether there is ventricular tachycardia or not. It's not talking about the number of ventricular tachycardia episode per week, per day, per no. But is there ventricular tachycardia or not? You know, in this situation, you can as well use logistic regression. But you see that we're going to run Poisson and run logistic. You're going to see that even for this situation, Poisson is better. It's a better model for this. So you're going to see some situation where you even use what do I call it? Use by you use logistic, it may be better for you to use Poisson distribution. So we have the data. Maybe somebody look at it. The table here is just a summary, you know, instead of listing the, because we have 52 of them. I don't list the data here. I just summarize it here. Somebody can run it and even summarize it. Maybe we should do it like that so that we can go. I don't want people to lose. I want, because exam, once you can understand with example, you can have, we will not have problem. So, what do you say? Any question? Okay, somebody should, there is a data file to say it. Somebody should read it. Let's first run that one. Read by will be coming, run it so that you see that table. That table I've checked. Yes, what do you, okay, I should allow you to share, okay?
You do allow enable share.
Okay, I've done that. To say.
They're doing a new one called this. Nothing like this. Did you see it?
Okay, that's okay. Go to the variable. You're going to see we have the serial number is just to list the subject. The two variables there are the presence of to say and treatment regimen. So see, go to the variable view and see the way we coded it. Okay, yeah, you see that for presence of to say, you have no, that is no to say, that's 0. No ventricular tachycardia, 0. Then there is, yes. We check the treatment regimen. You see that treatment regimen 2, there are 2 treatment, 1 and 2, but we don't know the treatment. We don't actually need to know the type of treatment. There are 2 treatment regimen for a particular disease. Even the disease we don't know. There is likely to be heart disease, but we have treatment regimen 2 coded as 0, 1 coded as 1. So we can record later. I will tell you the reason we coded it like this. You know, I want us to cross-tabulate. Before we cross-tabulate, Dr. Wazo was asking about coding and dummy variable. Whenever you are doing regression with variables that are not continuous or that are categorical, let's say categorical, no, they are categorical. Because they like sex, male, female, like this treatment regimen 1 and 2, it may be different name for the treatment regimen. They are categorical variable. You want to do regression, any form of regression, you just have to create dummy. So creating dummy means that because the computer, because what you want to achieve is that, oh, this category is if it's male and female now, you may choose one. Is the person a male? Of course, if the person is a male, it's not a female. If you choose, you can decide to choose female. If it's a female, if it's a female, it's not a male. So you can choose, if you want to choose the person a male, put the male forward. We code all the male as 1 and the female as 0. We can code all the female as 1 and the male as 0. Yes or no, you can code yes as 1, no 0. You can code yes as 0, no as 1. It doesn't really matter. It depends on the direction. And that's what we want to first of all look at the direction. What informs the type of the way you create the dummy. Because this one is very, very important. It's not just enough to bring result out now. When you bring result out, when you want to do it personally with your own work, you are stuck. Because there are some rudimentary things that you didn't understand. Now, if it just happened that in this situation, the two variables that are involved here, both of them are categorical, but there are two categories. It's two options. So whenever you are creating dummy, the number of dummy you create for a variable is the number of category of the option minus 1. So for each of them now, since there are two categories, like to say yes or no, the treatment regimen 1 and 2. So since there are two options for each of them, we are creating one dummy for each of them. So in that case, you make one of the category a reference, and that one will be given 0. And you now use the other one as 1. So what is looking at that whenever you make one 1 and the other one 0, when you are running your analysis, the attribute, what you are trying to say that how many times this person that I have said is 1 will likely have the attribute, the outcome, more than the person, more than the person that are coded 0. So, like for example now, if I make male 1, female 0, I'm trying to say the interpretation of my result will be how many times male is more likely to have this attribute than female. That's why I coded male 1, female 0. But what will have influenced me is that for that will have been that I've run the initial analysis, I've discovered that more of male have the attribute than female. But if more of female have the attribute than male, and I coded male 1, female no, try to see how many times male are more likely to have more likely. It will give you 0 point something, it's not up to 1 time, it's less than 1. If the lady tells you that, look, the one you make reference with is female, they are more likely to have the attribute than the other one. So it may influence you to, okay, let me reverse my coding so that the interpretation, because it's the same thing, though, so that it will be easy to interpret. I will now code the female 1 and male 0. So just know that whenever you are doing dummy, you are creating the dummy, the number of dummy you create is number of the category of the outcome of the variable minus 1. So that's that you are creating dummy for 1. You are using the other one as reference. But if you are having 3 categories, like for example, socio-economic status, upper, middle, lower, in that situation, you must use 1. If you want to create dummy, you use 1 as reference. The other one. But the issue sometimes the computer, when you use 1 as reference, you now create dummy for the other 2. So you are creating 2 dummy for 2 categories. That's why I say the number of dummy is number of category minus 1. And I can show you I think yes, the next examples we will talk much about the dummy because there's a variable there that has yes, about 3 categories, yes. So we're going to see there's a variable that has 3 categories in the next, not this example. We'll talk much about that. I don't know if you have questions concerning the dummy issue. I just explained. If you have any, we'll still talk about it later. Dr. Wazo, is he there?
Okay, yes, I think it's clear.
It's clear. Don't worry. When we do it again, also. Yeah, that's fine.
Yeah, maybe
your network is not good.
Yeah, by the time we start, like we're having to create like 3-4 dummies. Okay.
Oh, okay. Yes, I was not hearing. Is it Dr. Nishino that is talking or Dr. Wazo? We could not hear because the network was bad. Your voice was blurred. Repeat.
Okay.
Yes,
okay, can you hear now? Can you hear me now?
Yes.
Okay, so I was saying that maybe as we forge ahead, so
we can't hear you. Just stop. Sorry, you cannot hear you. Your network is bad.
101 for me. Hello?
Yes.
What?
Yes.
Okay. Okay. Is it better now?
It was
Is it
better, but
better?
later it became it's better, but when you start talking, it became blur. Yeah, talk.
Okay, so I was saying that maybe as we forge ahead, I will now see more, in a situation where maybe the dummies, we may need to create like 3 dummies and different combinations.
The next example, I think there are 2 dummies to be created.
It's okay.
I know what you can even open, because in some example we have done before, we created, and another thing is that sometimes also you may not even need the computer can create the dummy for you.
Okay, okay.
Yes,
That's beautiful.
especially when when you are doing all these categorical issue. If it is linear regression, yes, it will not. But for logistic and this Poisson, there is a place you can even say, okay, you select, you make this one the last. We'll show you the way it will create it for you. It will arrange it. It will.
Okay.
You understand it better. People that were here when we were discussing, when we workshop on ANOVA. We talk about contrast. We use contrast. The dummy is like the contrast also. The way the computer handle is like the contrast. If you just make one constant and now try to relate the other one with it. Okay. Let's first of all explore this data. Go to analyze and go to crosstab. Let's see the initial table I showed you at time. Let's see the way it comes out.
Crosstab.
Yes. Yes, that one will be the outcome. To say will be the outcome. The column. That's column. Presence of to say we go to column.
Treatment is.
Because that's the outcome. Treatment regimen will be row. So let's see. We don't even need it. Well, if you want to put certificate, let's just see the percentage. Let's see the go to column. Yes, cell. Yes. Show row for us. Yes. Though if you put the chi-square, it may, I think it's significant, but we are not interested in that one now. What we are interested in is to have a table to see. You can show us the results. Yes. Scroll down so that we can see that cross tabulation. Yes, that's great. You see the total is 52. Can everybody see? Can everybody see? If somebody see, let me know. Apart from the owner or the okay.
Yes, we are seeing. Yes, we are seeing it.
Yes.
We can see.
Okay. If you look at it, all of them, the total is 52. And
32.
yeah, and the total with treatment 1 regimen is 32. Treatment 2 regimen is 20. And the people total that have the fibrillation is 30. And people that don't have the fibrillation is 22. You will see if you look at it, percentage of people that have is higher in which group? Is it among the treatment 2 or treatment regimen, treatment 1 regimen? The percentage.
Yes, sir. Treatment.
Treatment, which treatment has the higher outcome of
Two.
yes,
25%.
75.
Yes. Thank you. Now I want to examine because there are some things I don't just want to assume. I want you to go and rerun this thing today, and let's remove the column row percentage and put columns as percentage. You're going to see something. Go back. Cross tab. Go back to that cells. Check the column, remove the row, and check the column here. Continue. Yeah, scroll down. No, you don't need to log out. It's already in that, it's already in the result window. Everybody is seeing it. No, next time you don't need to. Once you run your analysis on result window, we are seeing the result window. Okay, look at the second this table now, the same thing. So from here now, which group has the higher something? So how can we interpret the table? Just like the other one. Which group have higher to say it?
Two. Both of them.
No, it's treatment 1. 77%. I mean, it's about the same.
Low.
Oh, it's about the same. It's about the same.
So now, this one actually, you know, the data has not changed, the same data. This one is giving wrong information. Because what 50% you are seeing here is telling you, out of the 30 people that have to say the fibrillation, how many of them are in treatment 2? How many of them are in treatment 1? It's 50-50 because out of the 30, 50 are in treatment 2, 15 are in treatment 1, making 50-50%. It's not telling you the proportion of people that have to say. It's actually telling you the proportion of people that have to say that are in particular category of treatment. Can you see now? So why I'm saying that is that by not knowing the right direction of your percentage, you can misinterpret. You may give impression that the attribute you are looking for is the same on both groups. Do you get it now? So it's a wrong direction. So that is why your percentage should be along your exposure. So since we have already put our exposure as the row, our exposure is the treatment regimen, 1 or 2, is the row. Our outcome is along the column, which is the presence of, to say, the pointers. So your percentage should be along the row. If you look at it, you say the percentage within presence of to say. Can you see now? Because the percentage is along the to say the outcome. No. So scroll up to the first one you did. Scroll up, you go to the first one you did. That is the right way to do it. If you look at it, see the count, the percentage within treatment. Are you seeing that? That is along the treatment, along the exposure, how many have the outcome? Among the different group of exposure, how many have the outcome? While the other one is say among the different group of outcome, how many are in specific different exposure group, which is not what you're looking for. Does it make sense now? So
yes, sir.
As that, but many people miss it. So when they are running analysis, they don't have that that logic. They miss it. So we have seen that the outcome we are looking for is more among the treatment group. 2. Now that will have influence. You can, let's see, go to the window now. Okay, before we run, don't worry. Before we now run it, okay, just stop sharing. Stop sharing. Yes, let me share my own slide because I just diverted so that we understand something. It's good for us to understand the logic of it before you start running it. So can you see the origin of this table now? This table you see here is from the constellation that is showing you that yes, here, if you remember, 15, yeah, and so 15 among the people that have well, I coded, don't mind me, the regiment. I just, the way I put yes or no, I use one as yes or no. Sorry, I will have just say regiment 1, regiment 2. Make it easier. Regiment 1, regiment 2. So now, what I want us to do is look at the table. Treatment 1. I put treatment 1 I did something here. If you look at this table, I want you to look at this table. If you remember when we did our logistic regression, how do we, if you remember, look at the model up. The model is logarithm of y is equal to b0 plus bx1, b1x1. You know, if it is linear model, it's going to be y is equal to b0. b0 means the intercept. Then yb1 means the slope for x1. But now, if you were to be, there's something, I don't know. Where did I put this? There's a slide. There's a slide. Is it that I deleted the slide? There's a slide I wanted to. Oh, sorry. Where? Maybe eventually I didn't save it. There's a slide I want for illustrate something. No. No. Okay, no problem. Well, what I wanted to say here is that for linear regression, it's going to be y is equal to, I want to do something. I want to write. For linear, I didn't put that slide. For linear regression, the equation is y is equal to.
You're not seeing.
Oh, sorry. You are not seeing. I share it now. Is it only Prof I cannot see? Everybody cannot see.
I can see.
I can see.
Prof, you
I can see.
Because I shared this something. What's that?
It's come. No, it has come.
Okay, maybe you're this. Beta 0, which is this intercept, plus beta 1 x1. That's linear. For logistic,
Natural logarithm.
yeah, logistic regression is going to be the y is going to be
Then log.
is going to be logarithm of probability of y p over 1 minus p is equal to b beta 0 plus beta 1 x1. This is what we call logit. You can call it logit. So instead of you, because why is like that? The linear regression is the real value you are predicting. But in logistic regression, you are not predicting the real value. You are predicting the probability because either it's there or not. No, it's two outcomes, two there or not. That's why you now code the two as a 1 is 0. So that's why what you now really now look for. I will not be explaining that because the logic why they use logic, we explain it extensively, and I show you in a slide of our logistic regression, you know how the transformation where they shoot that one. Then where I'm going to for Poisson. For Poisson, it's going to be logarithm of y. Can you see log y is equal to beta 0 plus beta 1 x1. Can you see the difference now? So linear regression, just the event you are looking for. If it's linear, the event will just be the value of the event is going to beta 0 plus the beta s b1 s1. Logistic will be the logarithm of the probability over 1 minus p, which is the log odd. P over 1 minus p is odd. Then logarithm of what is called logit is the logic is equal to this. So it's logit you are looking for here. Logit. And logit is equal to this. Log P all over 1 minus P. Why this one for Poisson? Logarithm directly. I don't know if you can see the difference now. Logarithm directly. Any question concerning this one I just explained here? It's clear. Okay. Now, if you remember, when we were doing the logistic regression, all we need to do is that this right side of the equation, you don't have problem with. Your headache is not the right side. Your headache is the left side. That link. So if you remember, when we were doing the logistic regression, we first of all model when there's y, when y without x. Yeah. We now model where y with x, but when the value of x is 0 and when the value of x is 1. You remember?
Yeah.
And that is what we did here also. You will see, this is the equation we are looking at. Because when you understand the logic, when you run it, it sticks. This is the equation you are looking at, logarithm of y. Now, where the y without x, y has value even when there's no x. You understand now? It's just like a way like I said that you are trying to see, even in linear regression, you got to see, okay, what is the weight of somebody, what is the blood pressure? You want to predict blood pressure and sugar intake and salt intake. Blood pressure is the outcome, salt intake is the exposure. But even without you considering analyzing salt intake, you can know what blood pressure is by calculating the average blood pressure. I don't know if you understand me now. That is the crudest model, because mean is the crudest model. You can calculate the average blood pressure. In the logistic, if you remember, if you want to know, okay, if it's logistic now, the effect of treatment on to say, either you use treatment 1 or treatment 2, 1 regimen or 2 regimen. The effects, you want to look at the effects. Removing treatment, what proportion, you can know how many people have to say. Forget about treatment or not treatment. How many have to say? I want to know if you are following me. I want you to talk. This is a workshop. Forget this online. How many have to say? Forget about treatment. How many have ventricular tachycardia?
30%.
Thank you, 30%. You can know the proportion of people that have the, you can say 30 out of 52 have it. I don't know if you understand now. So that is it. So if you look at the 3 level of calculation you calculated, is the first one is when you are considering the outcome without the exposure, even apnea, you use the total. Can you see? That's the proportion. That's one that correlates with the mean in continuous variable. You just know the mean of something. That's the way you summarize continuous variable now, the mean. But if it is categorical, you summarize with proportion, percentage. What did you say?
So that last statement you made, can you just repeat it?
Which one? I said when you want to know the outcome, what the outcome is, even without even considering the exposure, which is the health. You look at the total here, the total. This is the total to say 30, 32, 22 do not have to say the everything 52. That's what I just said.
Okay.
So if you remember, in summarizing qualitative data, you use proportion. Is that not so? While in summarizing quantitative data, you use mean. So it's proportion that corresponds with the mean. Because when we are dealing with logistic or Poisson regression, they are discrete distribution. You are using proportion. The outcome is actually, thank you. Is not the outcome is not continuous. You understand now? So in that case, If you remember what I just illustrated now, I said that for logistic is the logarithm of odd, while for Poisson is the logarithm of that y directly. So how do we differentiate it? On this table now, if let's say that first one, I want to know if you remember that time when we're doing logistic, if you want to know, predict the value of y, even without x, we say 30 over 22. That would be the odd. I will not go into how it works like because I explained it in the slide when we're doing. I will not talk much about that. 30 over 22, that is the odd. You know, if you want to say what is the proportion of to say that's 30 over 52. What is the y minus that proportion will be 22 over 52. So odd is p all over 1 minus p. That is 30 all over 52 divided by 22 all over 52. You know 52 we cancel out 52. Just say 30 all over 22. The odd is 30 all over 22. Do you get the picture now? But here we are not talking of the odd. The Poisson is looking at the proportion itself. 30 over 52. I don't know if you understand. So that is why without x, logarithm of 30 over 52. Can you see now? So if you calculate, if you divide 30 over 52, look at I did it on the table here. Frequency 30, total 52. 30 over 52 is 0.570. Logarithm of it will give you this. If you go and you can use Excel or calculator to calculate it give you minus 0.550. Can you see? So, you know, in this model, that when you consider y without x, logarithm, the equation will be logarithm of 30 over 52 is equal to b0 plus bx minus b1 times 0, because you are not considering x there. X will be 0 in that equation. Can you see now? So it will now become b0, the intercept will be this. The intercept will be this. So when there's no x, the intercept, the lowest value what you get, the best you get for it will be, you can predict is the intercept without x. I'm explaining this, just remember this figure there. When we run, you're going to see the same thing in SPSS. You're going to see the same thing. Now, let's now look for treatment regimen. Now, when treatment regimen 1, which is 0, we have coded treatment regimen. If the treatment regimen is 1, I want to make it 0 because there are 2 treatment regimens. We have created dummy. One has to be 1 and one has to be 0 to be a reference. So if we make, why did we do that? Because we have found out that treatment regimen 2 have the attribute more than treatment regimen 1. I don't know if you understand me now. Sorry, I just this one. I just want to this regimen. So that this is 2. This is regimen 2. This is regimen 1. Yeah, so that I like it live so that people will conceptualize it. So we have made students, if we now look at in a situation where we are considering treatment regimen, regimen 1 now, which is 0. So it's going to be logarithm, natural logarithm of 15 out of 32. Can you see? Over 32 is equal to b0 plus bs times 0. You know, the value of it is 0 also. You know, the value of, though there's x now, but the value of the treatment here, we are put it at 0. That's why this x will still be 0. So when you, 50 over 32 will give you this, the logarithm will give you this, 0 minus 0.75769. Can you see? So B0, you will see that the intercept, when you are not considering x, is different from the intercept when you are considering x. Yes, I mean now. If you remember when we run our logistic regression, similar thing happened like that. It can also give you blocks is equal to 0. That give you block 1, if you remember. It give you 2 block. Block is equal to 0, also give you block 1. Now, when you now come for treatment regimen 2, that is, if it is 2, which is you code it as 1, this is this one. The logarithm of 15 over 20, can you see 50 over 20? Then BO plus this. You know, the value of B1 is 1 here. BX is 1, it's not 0. So when you now put it, the logarithm of this is 0. When 50 over 20 is equal to 0.75. Logarithm is minus 0.282768. When you now bring it here, so that shows that B0 plus B1 equal this. So if you remember, if you mean now, you substitute, we have already calculated P0 here for this one. You are not using this one without is this one. This one. So when you put the value here, so you change, you rearrange, you move this one over, you know, is minus here. You know, if you change something from it, it will become plus here. You know, it will become plus. So you now, if something is minus here, you cross over, it become plus. If it's plus, it cross over, it become minus. So when you do it, you now remove this from this. This one, it will give you this. So the B1 is 0.472. Now, the odd ratio here. The odd ratio here now. Now, when you are finished with this, beta doesn't make sense. What this one means is that for this, anybody that have anybody that use treatment regimen 2, yes, I mean this is increase in the logarithm of y. It's not the value of y now, logarithm of the probability of y per unit increase in the in x, per unit increase in your exposure. Yes, I mean now, log per unit increase. So that is the logarithm per unit. When you say per unit, so you know anything that is on its own is over 1. So you try to say that B1 is equal to 0.47 over 1. For you to now know how many times this person that use regimen 2 is more likely now to have the attribute more than regimen 1. You have to change it to opposite of logarithm to be antilog, which is exponential. So what we are saying now is that you are trying to say, okay, the ratio now, you know, antilog exponential B0 plus B1 is the one for this one. Is for the people that are regimen 1. How do you compare how many times the one that are in regimen 1 are more likely than the one that are regimen 2 numerator. Regimen 1 is this one. Can you see? So exponential of this, you know, combination of these two is not only this one, a combination of these two. Can you see? Yeah. The value, look at it now, over the one for this one. So if you do it, it gives you this.
1.8.
Yes, 1.5. So if we now calculate, yes, it now give you 1 point. Because when we do the antilog for each of them, these are the value for the antilog for this and this. We divide it. Another way of doing it is that you can first of all minus it. You will not divide before you calculate the antilog. It gives you the same thing. Come and see. That's what I did on the table here. So because the logic behind is that you know that in the natural scale, the normal scale, when you are comparing, when you are relating normal scale and antilog scale and logarithm scale, addition in normal correspond to multiplication in logarithm. Subtraction in normal scale correspond to division in logarithm. I think with them we did that when we were talking about logistic regression. Remember, I showed you a scale that the logarithm, the addition of two logarithm. When you say log A minus log B is the same thing as the division of those two values, the logarithm of. If you say log 6 minus log 2 is the same thing as saying log 6 divided by log 2. That is log 3, 6 over 2. 6 over 2 is 3. Log 6 minus log 2 is the same thing as log 3. Can you see? Log 2, 6 minus log 2 is the same thing as log 3. But in the natural scale, if you say 6 minus 2, it gives you 4. But logarithm of 6 minus logarithm of 2 is the same thing as logarithm of 3. So we only know minus and division. So that's why if we do it, I try to do it before I calculate the antilog. Before we calculate the antilog, you divide. But if you try to do it, no. If you do it after you calculate the antilog, you divide. But if you want to do it before you calculate the antilog, you remove. And you see, it gives you the same answer. As I remove this one from, I calculate the antilog. It's the same thing as calculating the antilog for each of them and then divide. So I think we have question concerning this one. Let's go and run it now. You're going to see all this value coming out. The only different thing between this and logistic regression is this. Instead of us looking for logarithm, here we look for logarithm of 30 over 52, 50 over 32, 50 over 20. That is, we are looking at the logarithm of proportion of the proportion of probability here in Poisson regression. But in logistic regression, we look at the logarithm of the odd. That is the probability over 1 minus probability. That's why I say 30 over 22, 50 over 17, 50 over 5. If, let's say we are doing logistics now, that's what we are going to do. But we are doing Poisson 30 over 52, 50 over 32. I don't know if you can differentiate between the two now.
I have a question.
Go on, sir.
So, yes, they are a little bit confused.
Okay, sir.
So I want to explanation. I want based on the equations.
Okay. Go on.
Yes, if we look at that first one, we say that B0 is minus 0.55005. Then if we look at treatment regimen 1, we say that the X there is 0. Does it mean that from treatment number 1, it was a placebo? That means X has no effect whatsoever. Since we are categorizing it, since we are giving the value 0 to it.
Okay, it has nothing to do with
natural logarithm. Placebo,
okay.
That means it has no potency at all. That's why, so we have two B0s here, B0 there, and B0 for the first expression.
Okay,
that's look at log B.
Yeah. Okay, yes, I understand that, Dr. Isaac. I think maybe probably why you are asking this question is that I don't think you were in our class when we did logistics. You didn't join us in logistics, right? Did you join logistics?
I joined though.
Okay, that was the one you now joined. That was the first one you joined later. You were not there in linear regression, right?
Yes, I was not there in the linear regression. I joined in logistic regression.
Okay, that was when you joined us back. So maybe somehow you mix it up somewhere. But I understand what you are saying. You are talking as a clinician. Yes, what you are saying is valid. But the issue here is that it has nothing to do whether it's placebo or not. It has to do with the way we created our dummy. If we say that we are going to make a group 0, in our equation it will be 0 here. I can return it if I do it now.
Okay.
I can make, when you are creating dummy, you make 1 1, you make 1 0. That's just it. It's just a designation. Okay. You understand me now? It's a model. Mathematics is a model.
Okay, I understand. If it is a dummy, I understand that logistic regression. I was using that one to look at this one. But
it's the same thing. That was what. It's even the same. That's why I wanted to go and show you. Bring the slide down.
I've understood. I
even wanted to go and bring the slide out even before you ask the question, because me, I like it when people get the logic behind something, you will not be confused. When you get the logic behind something, it makes it easier for you to conceptualize. So there's nothing. Let's just look at it. Look at this is the same thing. If you remember, this is what we use for the logistic. Can you see now? What is the difference between, look at similar thing. You look at it now. This is logistic. You see logit y is logarithm of odds. Look at the equation now. The equation is logarithm of p over 1 minus p. That's why where we are doing p over 1 minus p will be here now. If you want to do for the yes, it will be 46 over 254. Look, that's what you see here. Can you see?
No, I've understood it.
No, it's not only you know. I want to explain for that there are some other people also, even though they didn't ask. No, some people will not ask questions. Even when they don't understand, they will not ask. But I just want to. So, can you see now? Is here is logarithm. Just know the difference between logistic and Poisson is that the logistic is logarithm of odd. That's the link function. Poisson is the logarithm directly. It's not of odd. The logarithm of the probability. It doesn't have to be probability anyway. The logarithm, because sometimes it can be the mean. The next example is the mean. This one is a, we say that this example we are using is an example, the one they call log linear in Poisson, because the example we just used, the first example we used is log linear. The next one is not log linear, because that one has both categorical and continuous exposure combined in that one. So in that case, it doesn't represent you cannot say, and the outcome also is not just is there not there. That one is rate how many of the outcome. So in that case, we'll be talking of the average of the outcome. So this first one now is closer to logistic, but it's good to start with it because once you understand from linear to logistic to Poisson, you have captured everything. And in our next, this is going to be on survivor. You're going to see that one is a little bit tricky because of the peculiarity of that data. And that is why I want people to first of all get acquainted with all these the regression, the common one, before you now go to cost proportional hazard regression that is looking at hazard ratio. Can you see? So it's related to this one that in different ways. So this is what I just want to, you see now in that one, I just say dash proportion. The proportion is a P. But here is odd, which is P over 1 minus P. Is it clear now? So the other thing I wanted to say concerning the question you are asking, if you look at what I did in that one also in the Poisson, it's the same thing here. Look at it. Why without X? We say first of all, this one is different from this one in the sense that this first one, both of them have beta 0, the same, but it's not the same beta 0. This is a beta 0 when there's no model. When there's no, you have not built any model. You are not involved you are not trying to predict with any variable. And I gave the example. If anything like for example now, here now is for this example I'm showing now is CVD, prevalence of cardiovascular disease. Even before, without obesity, without anything, you can predict, you can try to say what is the rate of cardiovascular disease. That is just to look at the proportion. You calculate the proportion, so it is percentage. If it is something is continuous, you calculate the mean. But when you now bring a variable in now, so that is but that variable, this second is B0 now. That particular exposure variable you have to when you code it 0 and when you code it 1, you have to do it differently. So this is intercept, because the intercept also will change. You know the intercept when yes,
it's clear.
Yes, when S is there and when S is not there, the intercept will be different. So I think it's clear. Any other explanation?
We are taking the first. That is, we are taking the first one as a reference. So exactly. That's what I understand.
Yeah, that's great. Any other comment? Any other comments? Is it clear to everybody? So let's go back to what we're running now. Since we have, so Ugo, show the something again and let's start. Share the data set again. Yes, now go to analyze. Go generalized linear model. Go to generalized linear model. No, you are in general linear model. Yes, then the generalize. The first option, yes, generalized linear model. So click on that one. So you click on custom, you see custom down. So there are different way you can do it right there. Click on that, immediately you did a distribution and this one come to distribution. Click on that number, change that. If you remember when I was showing the generalized linear model, there's a table I was using. When I was talking about it contained three parts: the random, the systematic, and the link function. So you remember the random, which is the outcome. This is where we describe: is it normal, is it binomial, is it Poisson? This is where it's a distribution. That is the random aspect of it. The distribution is Poisson. Go to click on Poisson. Yes. Now come to link function. You know, we talk about link function also. You know, log, thank you. You know, if it is normal now, the link function will be identity. Now click on response. No, go to the, you are just finished type of variable model. Click on response. And your response variable, we already said, is the presence of to state. Yes, just move it to move it. Great. Now click on predictor. The treatment is the factor. Can you see? You're going to see in the next one example I'm going to use, we have two types. You're going to see, don't worry. The covariate, the one that are continuous will be covariate, while the one that categorical will be factor. Okay, move to model. Now, what I want us to do now, don't move yet. No, don't change it. It's the main effect. It's only, you cannot talk about it because there's only one factor here. Now, I don't want you to click it now. This is the treatment, the exposure. You want to first of all do that baseline, the first one without involving the X. I want us to run it. Click on estimation. Estimation. There's estimation after model. Click on estimation here. Now, you go to model-based estimator, robust estimator. Well, let's check. Click on robust estimation. Actually, you can use any of them, but sometimes people, yeah, let's use robust estimator. Then, okay, go to statistics. There are a lot of things here, but some of them can be confusing. Click on statistics. Now, click on include exponential parameter. Now, if you look at this confidence interval 95, but if you don't click on include exponential, down is down, 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 down. Include, it will not give you the odd ratio. It will just give you the confidence interval of the word statistic. Okay. Okay, I think that's all. Email. Click on that email. I don't think that one is there. Just click OK. Click OK. Yeah, just say yes, because it said that we didn't put the main effect. Yes. Just don't worry. Just say yes. We'll come back to do it. Just click yes. It will go. No, yes. Share the result with us. So yeah, scroll down. Is the last table? Yes, I'm interested in all those other ones. Most of all those things you see here, you see square, all the chi-square is the same thing, like a logistic. Some of those things, they are almost the same. But what, look at the table. You see, you remember, beta, this is only intercept. It just shows because we didn't put in model. We just want to first of all run without this thing, without the x. If you look at the intercept, if you remember that 30 over 52 we calculated, and when I calculate the logarithm is minus 0.55005 we got. Can you see that what you see here? Right? If you do the exponential, it gives you 0.577. So actually that is the same value for if you just divide 30 over 52, it gives you 0.557. If you do the logarithm of it, it gives you this. If you do the antilog, it gives you it back. So this is just the model. So, and it's just telling you that at least this is the prediction, the best prediction it can give without, that is, if you are to ask now, what is the rate of, what determine, what is the rate of to say? You know, oh, it to say is 0.557%. That is the people that have this. So that's all. Now, let's now go back and go to analysis. I want to know what you need to do now is to put that model there. That's all. Run it. It gives you the result you are looking for. General linear model, general linear model. No, every other thing. Everything is already in place. Just go to model. Everything is in place. We are already go to model. Click on the model. Then move that treatment into the model as the main effect. Click OK. Click OK. You have not. No, okay, yeah. Okay, click OK. Yes, scroll down now. Scroll down. Yes. Yeah. So now you see, can we see the result? You see that you see the intercept. Of course, the intercept has changed. If you remember, the other intercept we calculated for it was this one. The second one we calculated when x is equal to 0. That's the intercept, the beta. Then treatment, what it does, can you see now? Treatment is 0, and now your treatment is equal to 1 is used as the reference. Treatment is equal to 1 is our our treatment, what do I call it? Treatment 1, regimen 1. Treatment is equal to 0 is our treatment regimen 2. That's what we coded as 0. I will tell you the reason I did that. The way, I don't know, the way the Poisson, the way the programming, the way it behaves is different from the way logistic behave. Normally, we are supposed to, will have just coded, since we know that the attribute we are looking for is higher among the people with the regimen 2. We'll have coded regimen 2 as 1 and regimen 1 is 0. But if you do that, when you run it, it switch it. It will now use regimen 2 as the reference. You usually choose the one you code as 1 as the reference. So that is why we coded it like this. So now, what is telling us now, if you look at the beta, What did you get that time for beta 2? That's what, if you look at the slide, that's what we got, 0.47. So you calculate the handle of 1.6. What did you get? At the odd ratio 1.6. That's what you get. So what is telling us is that those people that receive regimen 2 are 1.6 times more likely to have to SAID than the people that receive regimen 1. You will see this is log linear analysis. Is a Fourier form of Poisson, that the categorical, the exposure is categorical, is log linear. You will see that straightforward is as if you have just done logistic regression. As if you have just done logistic regression. Now, I don't know. I know that this is to 9. I don't know if there's any question, because we still have other that we cannot run that one today. Tomorrow, no, we have already talked about theoretical aspect now, no long talk tomorrow. Just to go directly, we still have 2 examples we're going to run that are different from this one. The one that is, you can call pure Poisson, not log linear. But I don't know. Can we just go and use this data and run logistic with this data? You'll see something. You will see, wait first. You will see that this is statistically significant. Look at it. The odd ratio is 0.0, the p-value is 0.039, and the odd ratio does not cross 1. It shows that it's significant. Go to, it's not under regression, go to regression. Regression. Let's run the same data with logistic, binary logistic. More presence of SAID are dependent. Then this one are covariate, treatment as covariate. Click on option. So, yeah, no, leave those one. See exponential B, confidence interval. Click on it so that I can give you confidence interval. Click continue. Click OK. Great. So scroll down to the results. You will see, can you see the treatment? Almost significant, but it's not significant. Look at p-value 0.051, and it's not significant. Almost, but whereas in the other one, so it shows that the Poisson regression has more power. So if the difference is there, you'll be able to find it more than logistic regression in this situation. Any question? Any question?
Yes.
Let's continue tomorrow.
Yes,
Can you hear me?
I can
Can you hear me?
Yes, sir.
The area I'm not very clear is when you went back to analyze and move treatment to model, how did you do it? Because we are so fast.
Okay.
When you included the treatment.
So that will be the first thing we do tomorrow.
Okay.
Yes, because we have already, because we need a lot of time to explain a lot of things. So now now it's practical. Tomorrow we start with it before we continue the rest.
No problem.
Because if we have to be going back on it now. And it's to 9. People are saturated.
Yeah, so that's so that we don't get
any other comment that may not be so. There are some comments you can easily answer. The one you made now, you have to go back and be explaining all those things. Yes.
The variable we are looking at now has 2 categories.
Which 2 categories?
As in the treatment has 2 categories and the outcome has 2 categories.
Yes.
But if we have a variable with more than 2 categories, can it be used?
Of course, can be used. We have already said that we create dummy, that's all. And even to create the computer will give you option to make the category to select it.
Okay, sir.
Thank you,
sir.
You're welcome. Okay, any other one? Okay, I think we can stop here.
Yeah. Let's continue.
Stop
Thank you very
sharing.
much.
Stop
Thank you,
sharing.
everybody.
Stop
God
sharing.
bless you.
Let me
you,
stop
sir.
this.